Okay, I guess you don't even know this, but I'm starting again. This is the second time I've done this one. It's giving me headache like nothing else. We're going to go ahead and do it anyway, just for you. So we're back to 6.3 and 6.4, which is more of collisions. Now, 6.3, we're going to introduce you to two new types of collisions. Well, we're actually just going to classify collisions into two different types. The first one being the inelastic or the perfectly inelastic collision. And in the perfectly inelastic collision, we're going to have two objects that are going to collide. We're going to stay in one dimension, but when they collide, they're going to kind of stick together. And that means that they're going to kind of bend and break and stick, and it's kind of like having two cars with putty on their bumpers. So when they collide, the putty sticks together and it squishes and deforms and everything else so that they'll stick together. That's the perfectly inelastic collision. And in a perfectly inelastic collision, you're of course not going to conserve kinetic energy, because some of your kinetic energy is going to have to go into making that change of formation of the putty or the parts of the two objects as they try to stick together. So we're going to lose some energy from the collision, some kinetic energy from that collision, perfectly inelastic collision. It is important that these objects stick together and become one object, essentially. So they become one mass. You start out with two masses, maybe going towards each other or in the same direction, but when they collide, they stick and become one mass. Mass 1 added to mass 2. In an elastic collision, we have two objects that are going to bounce off of each other perfectly without any deformation or loss of energy. And so in an elastic, a perfectly elastic collisions, we're going to have a conservation of energy, conservation of kinetic energy in particular. In both of these collisions, we're going to conserve momentum, because momentum will always be conserved. And so we will go ahead and say that we will conserve momentum all the time in both of these collisions. Now, what does that mean? In the perfectly inelastic collisions, we're going to have momentum of object 1, or mass 1 times velocity 1 initially, plus mass 2 velocity 2 initially. The two initial momentums of the separate objects are going to add together to give your total initial momentum. And that has to equal the total momentum at the end of the problem, but since they're stuck together in a perfectly inelastic collision, you're going to get mass 1 plus mass 2 at the end, added together times the velocity final, which will be the same velocity for both of them. So, because they're stuck together. So you solve for the final velocity and you get this equation that's just the initial momentums divided by the total mass at the end. It's a fairly simple equation for that final velocity of the stuck together objects. In active figure 6.10 here, we can see these this inelastic collision. We have two balls. We start them going, and it's going at 10 meters per second, then all of a sudden it's going at 5 meters per second because it has twice as much mass because it's stuck to the next ball, right? And we can change the velocities, and we can give this other one some velocity, and we can change some mass here and see what happens. And we start it, right? So they're coming towards each other, and we can see that they stick, and it has some final velocity. And the total momentum of the system before will equal the total momentum of the system after. It is completely conservative of momentum. Kinetic energy, not so. And in fact, they show us this, or we demonstrate this in example 6.4. Example 6.4, we have two cars going towards each other. Velocity 1, velocity 2 are equal velocities but opposite directions, equal in magnitude, opposite in direction. But the truck weighs more than the car. The truck's 1.8 times 10 to the 3, and the car is 9 times 10 to the 2. So the truck is twice as heavy as the car. And what's going to happen when they collide? Well, we assume that the truck's momentum is going to win it over, because the truck's momentum to begin is much bigger than the car's momentum, going in the right-hand direction. That's what happens. But as far as equations go, since this is an inelastic collision, they stick together and become one object, we have momentum initial equals momentum final. So we calculate the individual momentums of the two cars, add them together, and do realize that velocity 2 for the car, second car there, is going to be a negative number, right? And that's going to equal these here. And so we solve that for the velocity final, plug in our numbers, making sure we have the negative 15 meters per second for the car. And we're going to get 5 meters per second for the final velocity of both of these together. In other words, they're moving at 5 meters per second in the right-hand direction, stuck together. In part 2, they want us to find the change in the velocity for each vehicle. So for velocity 1, the change in velocity is final velocity minus initial velocity. Get the signs right. In this case, it's a negative 10 meters per second for the bigger car. It slows down by 10 meters per second. For the smaller car, starts out at negative 15 meters per second, ends up at 5 meters per second. You take the difference there, and it's 20 meters per second difference. So the smaller car has a much bigger change in velocity, magnitude-wise, even though the direction is in the opposite direction. And that's why it's a worse experience for them, because it's a bigger acceleration in the same amount of time. The change in kinetic energy of the system, we calculate the kinetic energies and then take their differences in the kinetic energy initial, kinetic energy final, and you get the total kinetic energy of the initial system is 3.04 times 10 to the 5th. The final kinetic energy of the system is 3.38 times 10 to the 4th. It's almost a 90% drop in energy. You lose so much energy in that inelastic collision, the bending and deforming of the cars as they connect themselves together, crush up and everything else. So lots of energy loss in the collision. Another classic example of a perfectly inelastic collision is what we call the ballistic pendulum. We shoot a bullet into a block that's just hanging from the ceiling. When the bullet enters the block, it gets stuck in there, and the block will swing upward with a momentum that is equal to the momentum of the initial bullet. And so you can also use this apparatus over here where you shoot a ball into this ball catcher and it swings up on a pendulum. It's called the ballistic pendulum, and you have the bullet has momentum at the beginning, but the bullet and block have the momentum at the end. So they actually are doing something different here. They're going to measure the height that the block rises up, because the potential energy of the block as it rises up through this height is going to be equal to the kinetic energy of the block down here at the bottom of the system. And from that potential energy equals kinetic energy, you can actually calculate the velocity of the block as the bullet embeds itself in the block. And then you can use that velocity to calculate the momentum of this entire block and bullet system when the block and the bullet are one. So that's what they do here. They use conservation of energy after the collision, so kinetic energy of the block and bullet to potential energy of the block and bullet. And that's just a swinging block, so there's no energy lost in that particular thing. They have a zero potential energy for the block and bullet, but all of it's in kinetic energy at the bottom. And then they have a zero kinetic energy at the top because it swings up and comes to a rest, and all the energy is in potential energy. They solve that. They get a velocity of the system when the block and the bullet are when the bullet embeds itself in the block, which is this 0.990 meters per second. Well, then they use conservation of momentum to say the momentum of the block and the bullet with this velocity has to equal the momentum of just the bullet with its original velocity, and then they solve that for the original velocity, and they get 199 meters per second, which makes sense for a bullet. About 200 meters per second is a pretty reasonable speed for a bullet. And that is conservation of momentum, where they used conservation of energy of the second part of the experiment to calculate the velocity and the final velocity in the first part of the experiment, so that they could use the conservation of momentum. Now, with elastic collisions, we have both equations of conservation. The first one, conservation of momentum, which is here. Notice it's different because we have separate momentums for each object before and after, initial and final, because they're not stuck together at the end. In an elastic collision, things bounce off each other and they stay independent. But if it's an elastic collision, then you also get conservation of kinetic energy. So you have initial kinetic energies over here, final kinetic energies added together. They have to be equal to each other before and after. And what they're going to do here is they're going to solve this second equation. They're going to solve it for the final velocity of one of these objects. I don't remember which one. But they just do some basic algebra here. They're going to take a difference of squares here, and then they're going to do some factoring. And then they're going to they're going to simplify down and they're going to get this equation 6.13 at the bottom of the page. And then they make it even simpler by assuming that the masses of each of the objects are the same. So it's like two billiard balls, right? And when you assume the masses are the same, then you get equation 6.14, which is even simpler because it doesn't include any masses. They all cancel out. And so that's kind of nice when we need to do an equation like a pool ball equation, right? So here we have some billiard balls. They have identical mass. They're moving towards each other. The initial velocity is 30 centimeters per second, negative 20 centimeters per second. So one's going one way, one's going the other. And then what is the velocity? What are the velocities of balls after the collision? Well, we have two equations we can use. Conservation of momentum, which is the first equation they use. And what they find out is that they have two things they don't know. The velocity final of both balls, they don't know. So they have an equation that tells us if we add the two final velocities, we get 10 centimeters per second, but it doesn't tell us what either of them are. There's an infinite number of possibilities that can do that, right? That can satisfy that equation. So then we use the conservation of energy equation that comes in 6.14, which is really quite simple as well. And there we find that if we take the difference of the two velocities, we get 50 centimeters per second. Well, there's only one number where if you take the difference, it's 50 centimeters, and when you take the sum, it's 10 centimeters. And so what you do is you add those two equations together, and you're going to get a cancellation of velocity 1 final, and you'll solve for velocity 2 final to be 60 centimeters per second. Keep track of your signs. Then you can plug that velocity 2 final into any old equation up here before that and calculate velocity 1 final. It's really quite straightforward. Now here's the tricky part. Two blocks and a spring. We're going to now put a spring in between, and these blocks are going to go towards each other, and they want to know the velocity of block 2 after it's hit the spring and it's still moving towards they want to know the velocity of block 1 after it's hit the spring and it's still moving towards block 2 with a slower speed of 3 meters per second instead of its initial speed of 4 meters per second. Well, it's really quite simple. Momentum is still conserved. So we plug into our momentum equation an initial velocity that they give us, which is the 4 meters per second, positive. The velocity, the initial momentum of the second block, which is going to be, we're going to use this negative 2.5 meters per second times the mass of the second block, which is given up here as whatever it's given as, 2.10 kilograms. And then the final velocity of block 1 is going to be the 3 meters per second. You can see it down here. The 3 meters per second that we want for that first block. And that will solve for the second velocity, the velocity of the second block after they've collided for just this short time. And when you do that, the second block velocity comes out as negative 1.74 meters per second. Then they want to know the compression of the spring, the maximum compression of the spring in the system. Well, in that case, you need to use energy because we don't know anything about momentum of springs. In fact, I don't even know how to describe a momentum of a spring. But I do know how to describe the energy of a spring, and that's where you have initial energies, two kinetic energies, and a spring energy. At the beginning it's 0 because it's just relaxed. And then you have the final kinetic energies plus the stretchiness of the spring, or this compression of the spring, 1/2 kx squared, where x is the compression of the spring. And that's the thing we're going to solve for, is that x. And when you do that and plug in the numbers, you get x, the compression of the spring is 0.173 meters. Now that is the end of section 6.3, and we need to get into section 6.4. This is actually a little bit tougher because we're going to go into dimensions. What if we start going in one dimension and then we bounce off the ball and we go off in some other dimension, some other direction? Well, it's really quite simple. The conservation of momentum equations get split into two conservation equations. One where all of the momentum in the x direction is conserved, and one where all the momentum in the y direction is conserved. And you got it. You've got to take your momentum vectors, and they have got to be now resolved into x and y components and put into these equations, so it's twice as much work. Don't you just love it? So let's take a look at this active figure. We have mass 1 and mass 2, and notice that the line of collision doesn't line up on their centers. So when we start this up, we're going to get this thing going, and then they're going to bounce off at funny angles. Notice something interesting. This looks like a right angle. Turns out that it will always be a right angle as long as one of the balls is sitting still and the other one is glancing off of it, and they're of the same mass and radius. It will always work out that way. But anyway, If we change the mass, we get different solutions, we get different things going on. Change speeds, we get different things going on, and we can get lots of different solutions here. We can also change the angle or the position of M1 so that it's much different. Start this thing off. We can go up here and get a different glancing collision, right? Notice that it's not always 90 degrees between the two collisions anymore, between the two lines anymore. So here you can see all of the components now of the velocities, and if you multiply each of those components of the velocities times the mass of each particle, then you're going to get components of momentum. And you're going to use these equations in both dimensions to calculate those conservations of momentum. Now, conservation of energy is still valid, but it doesn't care about direction. You'll still be able to use it, but it just doesn't care about direction, so it's just one equation. You have to work twice as hard in the momentum section, but you still have the same thing going in the kinetic energy equation, conservation of kinetic energy. So here is a collision at an intersection, and in this particular case we're going to have two cars colliding. They tell us their masses, they tell us their initial speeds and the directions, and then they want us to find the magnitude and direction of the velocity of the wreckage after the collision. Well, that would be nice, because if we find the magnitude of the velocity afterwards, then that'll tell us something about its momentum afterwards, right? And they're going to stick together. It's going to be a perfectly inelastic collision. They tell us on the problem. So let's go take a look. We have to add together all the momentums in the x direction. So it's going to be mass of the car times the velocity of the car, right? And let's see, was the truck sitting still? I don't remember what it said it was doing. No, it's just that okay, so I remember now what's going on. So in the x direction, the car is moving in the x direction initially, but it's not moving in the y direction initially. But the other car is moving only in the y direction. So we have the van that's moving in the y direction. So in the x direction, we're only dealing with the car initially. So with the mass of the car times velocity of the car, that is the initial x momentum right there. 3.75 times 10 to the 4th kilogram meters per second. However, in the final, after the collision, we have the mass of the car plus the mass of the van times the velocity final times the cosine of theta. And so this equation is going to have to be equal to the final velocity, which is 4 times 10, oh no, sorry, the final mass, which is the sum of the two masses, so it's 4 times 10 to the 3 kilograms, times the final velocity cosine theta, right? So there's our total momentum initially in the x direction and our total momentum finally in the x direction. These two things have to be equal to each other. And you can see that when you set them equal to each other, you actually have an equation you can solve for velocity final times the cosine of theta, but you can't solve it for just velocity final because theta is an unknown. So we have two unknowns here we've got to figure out. So we just leave it as it is and we move on. In the y direction, we have the van initially, and then finally we have the car and the van together. And it's going to be sine of theta according to our drawing on the previous page for that direction of the final velocity. And then you set those two equal to each other and notice that you get an equation again that has velocity final and sine of theta. Well, in the case of having sines, thetas, and cosine thetas in an equation, sometimes it's easier to get rid of the velocity than it is to get rid of the theta, because if you divide the first equation, equation 1, by the second equation, actually I think they do the second equation divided by the first equation, then you get the tangent of theta, because it's the sine divided by the cosine, right? So they divide the first equation, is that right? Tangent is sine over cosine, right? So that's the second equation. Oh, there we go. So we got second equation divided by first equation. Notice that the velocity finals just cancel out. Velocity final in the second equation, velocity final in the first equation. So they don't show up here, they cancel out. We get that the tangent of theta is equal to 1.33. Well, to solve that, then you just take the inverse tangent of 1.33, and you get 53.1 degrees. So now we know which direction it's going, and we know what theta is, so we can plug it into one of these equations up here. It doesn't matter which one. Plug it in up there, and you'll calculate velocity final. And they do that, and they get 15.6 meters per second. So now we know that the car and the van, when they're stuck together, are going 15 meters per second at an angle of theta 53.1 degrees relative to let's see where that angle theta was. Theta was taken from the x-axis up to here. So a 53-degree angle up here, 15.6 meters per second. So all they're doing is they're doing the conservation of momentum twice, once in the x direction, once in the y direction. And if you need to, you can do conservation of energy, and it doesn't matter which direction you do it in, and you're good to go. So, homework 6.4. Homework 6.4 is take a look at it. So homework 6.4 is, it's got 6 problems in it. So we have an archer that's shooting an arrow that is sliding in his direction. So an arrow is going to hit a target. It's going to be an inelastic collision. You can use conservation of momentum, and that's it. But it's linear, so it's no big deal. Then you have a railroad car moving, and it collides and couples with 2 coupled railroad cars, each of the same mass, moving in the same direction at a speed v2. So another inelastic collision, you can use conservation of momentum only. Problem 3 is the ballistic pendulum. That one shouldn't be hard since we did an example of it. But problem 4 is one of these problems where we're doing a glancing collision. Now notice that they're saying that it's a perfectly elastic glancing collision, and the green disc is initially at rest and the other one hits it and has this initial speed, and they tell us the angle phi here, 56 degrees. They also tell us that these shuffleboard discs are of equal mass, and we can assume that they're also of equal radius. Well, what did we say this total angle would be here? We said that if you have equal mass, equal radius, glancing perfect elastic collision, that angle will be 90 degrees. You can actually figure out what theta is right away. Actually, they tell you what theta is, and that's nice. So they tell you theta and phi, I guess, and so that does make a 90-degree angle, which makes sense. We like that. Hoping that we were being clever by figuring it out, but I guess we weren't. But you're going to calculate. It's easy to know what the momentum is in the y direction, because this one's moving in the x direction, this one's not moving at all. There is no momentum in the y direction. So there is momentum in the y direction after the collision, and those two y momentums are going to have to cancel out to 0. So the momentum, or the velocity of this thing in the y direction times its mass, has to equal the velocity of this one in the y direction times its mass. Right? The other thing that we have to know is that, the other thing we have to know is that the velocity of this puck in the x direction times its mass, plus the velocity of this puck in the x direction times its mass, has to equal the velocity of the initial velocity of the orange puck in the right direction with its mass. So you have to add these two x direction momentums. It has to equal this one's momentum. Question 5 is a tutorial, and it's another ballistic pendulum, but you're going to use a kinetic energy thing as it falls down this distance, and it's going to go a certain distance here, and it will step you through how to do that. And then in problem 6, you have a 28-gram object moving to the right. It overtakes and collides elastically with this 6-gram object moving in the same direction. So same direction to the right, call them both positive. Find the velocity of each object after the collision. It's an elastic collision. You conserve momentum. You conserve kinetic energy. You can solve these equations when you get all those equations written out and all the proper things plugged into them. So that's all we have for you today. I will see you again later.